Well, Harry, your unit is out of tolerance at 1.3 volts.
But I measured it using this wonderful meter at 1.25 volts.
I really don't care. I measured it with this meter and it came out 1.3 volts.
Well, I hate to break the news to you both, but you're both wrong. I measured it at 1.27 volts, just within tolerance. Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel, and today we're going to be talking about measurement uncertainty. Now, we all have the tendency to think that when we measure something with our beloved instrument, that this value is exactly what it is. And if someone else gets a different value with their instrument, then we're all puzzled. Well, I measured it at thus and so. How come your measurement is different? Hopefully this video will help you understand why this might be and how to avoid some of this uncertainty. If you have questions or comments, please feel free to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe. So why the difference in these measurements? Well, let's go see. There are three basic sources of measurement uncertainty. The first is test instrument tolerances. The second is test instrument calibration. And the third is circuit loading. So let's talk about each of these one by one. Well, let's face it, there's no such thing as a perfect measuring device. True, some are more perfect than others, but none are perfect. My specialty in the U.S. Air Force was Precision Measurement Equipment Specialist. I was stationed at Pease Air Force Base near Portsmouth, New Hampshire in the mid-1970s. We maintained all of the measuring devices on the base, whether it was electronic or mechanical or optical. And this included calibration and repair. Even in our climate-controlled lab, the instrumentation we used to calibrate the measuring devices on base, well, they weren't perfect either. We had to send our instruments off to depot for calibration where instruments with more accuracy lived. Now, one of the first lessons that we learned was the difference between precision and accuracy. Precision meant that we could hit the same spot every time. It might be way off target, but we could hit the same spot every time with real precision. Accuracy is hitting the right spot. And what we want in our measurements is both accuracy and precision. Now, every measurement device has a specification for accuracy, and this specification can be stated in many different ways. And two of the more basic ways that this is stated are in terms of its reading and in terms of the full scale reading. Now, most often these terms will be in percent, so let's try to understand these just a little bit more. Well, the first one is the easiest to understand. After parsing through the mind-numbing specification sheet on my Siglent oscilloscope, I find that it is a plus or minus 3% device, assuming that the human reading the screen wildcard is done perfectly. Well, good luck on that one. What this means is that the voltage that I'm reading could be 3% high of the actual voltage, or 3% low of the actual voltage, or anything in between. So if I'm reading a voltage of 3.4 volts using this oscilloscope, then the actual voltage could be 3.4 divided by 1.03. Now that's 1 plus that 3% percentage, which gives us 3.3 volts. Or the voltage actual could be 3.4 divided by 0.97. Now that's 1 minus that 3%. Which equals 3.5 volts, or anything in between these two values. Well, speaking of an oscilloscope, there's also the time accuracy of the horizontal trace. In the case of the Siglent scope, it is plus or minus 25 parts per million. Well, if this doesn't make sense to you, I have a video on this, the link for which is up in the corner. I don't want to take the time here to explain it because I want to keep this video as short as possible. And then there is the digital multimeter. Again, we often assume that the numbers on the screen are as true as the gospel, but digital multimeters are just as prone to error as their analog cousins. They replace the human reading the scale error with digitization error. Instead of some person with their eyeball on a meter scale, we have some electronic device with its virtual eyeball on its own virtual scale, making its own errors in reading the value. Looking at the specifications of a digital multimeter, we can get a little confused trying to understand what they mean. They begin with the accuracy in terms of percent of reading and then add to this the digitization error. I made a video on understanding these specifications and what they mean, and I've put a link up in the corner for you. The second one is just a little bit more obtuse. Not every measurement instrument rates its accuracy in terms of percentage of the reading itself. In many cases, it rates its accuracy in terms of its full scale reading. If I'm using this lovely vintage RCA WV518A analog multimeter, then the manufacturer's original specification is plus or minus 3% of full scale when measuring DC volts. Well, what this means is that if I have my meter connected to a perfect 10-volt DC battery, I would have to use the 15-volt scale. 3% of 15 volts is 0.45 volts. So in reading this perfect 10-volt DC, I could read anything from 9.55 volts to 10.45 volts and still be within its tolerance. The actual error in the reading itself would be 100 times 0.45 divided by 10, which is the voltage that we're actually reading, is equal to plus or minus 4.5% when measuring a 10-volt signal on a 15-volt scale. With an analog meter, there are two other things that contribute to measurement uncertainty. The first is meter zero. In other words, when nothing is connected to the meter is turned off, and it is physically in the same position it will be in when making the measurement. Is the needle resting on the zero? The second is parallax. Are we positioning ourselves properly to read the value off the scale? Now, I go over this whole business of accuracy, reading an analog meter movement in my video on this subject. I put a link to that video up in the corner for you. The point here is that even if we do everything right, the best we can get in a measurement is within 3% of the full scale reading for any scale. On the 500 volt scale, this would be plus or minus 15 volts. Another such case in point is this way awesome Bird 43 inline watt meter. Now trust me, this thing ain't cheap. This model has been around for many, many, many years and has served as, well, almost an industry standard. And while it is true that I used to calibrate these things when I was in the Air Force, you know, you can still buy them brand new today from the manufacturer. Now, you change the frequency range and the full-scale power reading by purchasing different elements which plug into the front of the meter. We use this wonderful and trusted watt meter and say things like, that transmitter has 35 watts out, and I know this because my bird says so. But if we look at the specifications for this watt meter, we discovered that it is rated at plus or minus 5% of its full-scale reading. Okay, so let's put this into perspective and see how this plays out in our measurements with it. Suppose I'm using my 50 watt element. Now 5% of 50 watts is 2.5 watts. Thus, if I'm measuring the output power of a transmitter whose actual power output is 35 watts, my Bird watt meter will report anything from 32.5 to 37.5 watts. On a 35 watt transmitter power, this amounts to 100 times 2.5 all divided by 35, or plus or minus 7.14%. Now suppose this is the only element that we have for this frequency, and I'm trying to measure the output power of an 8 watt handheld transceiver. If that HT is actually outputting 8 watts, then my bird might report anything from 5.5 to 10.5 watts. Now, 100 times 2.5 all divided by 8 gives us an accuracy of plus or minus 31.25%. All of a sudden, this doesn't look so wonderful, does it? By the way, in a planned upcoming video, I will be showing how to measure this output power with better certainty. I just had to stick in this little teaser here. So even if everything is done perfectly, the measuring instrument that we are using will only report the measured value within a certain tolerance of accuracy. And all of this has everything to do with a properly calibrated instrument. Well, what is all this calibration business? Well, you know, we all have them. A meter, an oscilloscope, a communications monitor, some sort of measurement device that we've had for years and years. Maybe we bought it new. Maybe we got it from a friend or bought it used off of eBay. The point is, it's been around for a while and we trust it to be right. The fact is that most equipment manufacturers will only certify their measurement instruments to be within stated tolerances for 1 year following calibration. Some might go as long as 2, but those are rare. Now here's a direct quote from the specification of my Fluke 179 DVM. Quote, "Accuracy is specified for 1 year after calibration at operating temperatures of 18 degrees C to 28 degrees C with a relative humidity at 0% to 90%. Most every company that has any kind of measuring devices have all of them calibrated on a yearly basis. In some cases, they gather them all up and send them to a calibration lab. And in others, the calibration folks bring the lab to the company's location and do the calibration on site. Each item that is calibrated is marked and logged. The average guy like you and me, well, we don't have the deep pockets to go through this process with our measurement instruments, so they languish as we live by faith in their accuracy, even though it might have been decades since the last time they saw a calibration lab. Now I need to answer the question, what is calibration and what is it not? Now I'm going to trot out my U.S. Air Force metrology training for all to see. Technically speaking, calibration is the process of comparing a measurement device against known standards to determine if the instrument is within its stated tolerances. The known standard against which it is compared must have an accuracy at least 10 times better than the device being calibrated. The accuracy of these known standards must be directly traceable to the National Bureau of Standards. If the measurement device that is being calibrated is outside its stated tolerance, then the correction of this condition is considered a repair, not calibration. With all of this said, does this mean that the measurement device that we rely on so heavily for accuracy is not to be trusted if it's been over a year since it was last checked? Well, no, I'm not saying that. What I am saying is that the assurance that it is accurate gets thinner and thinner the longer it has been since its accuracy was checked against a known standard. It might be just fine, but then again, it might not be just fine also. Now the last item to consider has to do with what your measurement instrument is doing to the circuit you're trying to measure. Every measurement device on the planet will always draw some current from whatever you're connecting it to. Now, some more than others. In some cases, this is quite intentional and even desired, such as the 50 ohm input impedance to the spectrum analyzer or the VNA. In these cases, the thing that we're measuring is often expecting to see 50 ohms, and the measurement would actually be an error if it wasn't there. But these are kind of special cases. Generally, we're sticking our measuring device into a circuit that is designed to operate on its own without the interference of some measuring device probing it. First, let's look at a few multimeter devices, such as this old analog multimeter. These used to be called volt-ohm-meters, or VOMs. Just a piece of trivia to chew on. If we look at the specifications, which for this one is no longer available anywhere, but if we look at the specifications or look closely at the meter face, there's a number here which is 20 k ohms per volt DC and 10 k ohms per volt AC. Well, what does that mean? Well, if I'm using the 15 volt DC range on this, the input resistance of the meter will be 15, which is a full-scale voltage range, times the 20 k ohms, which is 20 k ohms per volt, which means that the input resistance of this meter on that scale will be 300 k ohms. If I'm using the 15 volt AC range, the input resistance of the meter would be the voltage of the scale, 15, times 10 k ohms, which is 10 k ohms per volt, which would mean the input resistance would be 150 k ohms. Now, most every analog multimeter is different. This Craftsman is 2 k ohm per volt on AC and 4.5 k ohm per volt for DC. And then we have this hardware store multimeter. Well, it's 2 k ohm per volt AC or DC. Now, with all of this said, the digital multimeters generally have a much higher input resistance. Now, I'm not saying that they have an infinite input resistance, but it's certainly a whole lot less of a concern with one of these than it is with the analog cousins. Now, these sorts of concerns do not just apply to multimeters. Consider an oscilloscope such as my Siglent. This one, like most oscilloscopes, has something on the order of a 1 megohm input impedance. And this seems quite sufficient, but in some situations this can still load the circuit in question. Now, also be aware of the capacitive loading of the input of an oscilloscope and other similar devices when working with AC circuits, especially when thinking of RF measurements. Now, you might ask, why is the input impedance of my measurement device even an issue? Well, let's consider a medium impedance circuit, let's say like 10 k ohms, which has 10 volts writing on it. Now, this isn't especially a high impedance, but it certainly isn't low either. Now, we take my old analog multimeter with its very respectable 20 k ohms per volt rating, and to measure the 10 volts, I have to use the 15 volt scale. This means that the input resistance of the meter is going to be 300 k ohms, and that sounds pretty respectable. The input resistance of the meter forms the output resistance of a voltage divider. So the 10 volts with an impedance of 10 k ohms is the input resistance of this voltage divider. So our meter will read 10 times 300, all divided by 300 plus 10, or 9.68 volts. If, of course, if it's perfect in its own tolerances. But being a 3% a full-scale meter, it could read anything from 9.23 to 10.13 volts. Now, you could reduce this effect by using the 50 volt scale, which would give us a 1 megohm input impedance. And that sounds great. It certainly would reduce the loading effect on the circuit. But you have two significant trade-offs to deal with when you do this. The first is that you lose scale resolution which will affect your ability to read the voltages precisely. The second is that it multiplies the measurement uncertainty from plus or minus 0.45 volts, which you had on the 15-volt scale, to plus or minus 1.5 volts because of the measurement tolerance of the meter itself. Now imagine what would happen with the hardware store multimeter that has only a 2 Ohm-per-volt input resistance. We would have to use the 10-volt scale on this meter. The input resistance would be 20 ohms. So now we connect this meter to that same circuit, and the meter would have to read 10 times 20, all divided by 20 plus 10, or it would read 6.67 volts if it is perfect in its own tolerances. This is a plus or minus 4% full-scale meter, so it's a lot worse than that. This isn't any kind of an issue when measuring something like a battery or the output of a power supply or the line voltage at a wall outlet, because the impedance of these things is very low, and the effect of even a low input impedance will have virtually no significant effect on the measurement. We are left with only the measurement uncertainty of the meter itself. Now, as I mentioned before, this isn't all about multimeters. This loading effect is a fact with any measuring device. In recent experience, a fellow engineer was measuring a voltage on a place in the circuit using his oscilloscope. He was wondering why the voltage was so very low. The problem was that this particular spot had an output impedance of 750 ohms, and he was using a 1 megohm input impedance oscilloscope with a 1 times probe. So how can we mitigate this? Well, we use a times 10 scope probe. Now the input impedance of the scope appears to be 10 megohms. And once this engineer friend did this, the voltage he was measuring looked a lot more like what he was expecting. So the three guys that we started out this video with could be absolutely right in their measurements depending upon the accuracy and loading of their meters. They could have easily gotten these three divergent readings even if they were using the same make and model of meter. The one guy's meter could be 1.7% low, and the other one 1.7% high, and the third, well, somewhere in between. But which one was right? The only way to know is to have each meter calibrated and its accuracy adjusted. Well, hopefully at this point you have a better appreciation for what's going on. If you found this video helpful, please click on the like and don't forget to subscribe to the channel. Thank you so much for watching. Until next time, toodle-oots.